Hello everyone, this is Maurizio, editor-in-chief of Power Electronics News, and I am here at PCIM showing in Nuremberg, and I have the pleasure to be here with Stephen Lee, product manager of Power Electronics Design Software at Keysight. Hi Stephen, welcome aboard. How are you?
Thank you, Mauricio. Thanks for having me today. Really appreciate it.
Thanks for your time. Everything is good? Everything
Yeah,
is fine?
yeah. Everything's good. It's an exciting time. A lot of things happening in the power electronics world. So, yep, very
Yeah,
good.
Power Electronics is everywhere.
Yep, you can't have life without it. So, so it's good.
So let's start. So I have prepared a couple of topics for you, Stephen. So let's start about talking about wide-band gap. Okay, wide-band gap,
Yep.
like gallium nitride, like silicon carbide. So how would you describe the current maturity level of both technologies in power application? Which are the remaining obstacles, barriers from technical, commercial point of view that could slow down the adoption for the next, for the markets in terms of automotive, in terms of industrial. So, please.
Yeah. That's a great question because every year it keeps changing. Actually, over the last 3 years, definitely see a lot of adoption of silicon carbide and gallium nitride. I definitely see silicon carbide as becoming the technology that's maturing faster. I think in general is the designers are having an easier time using silicon carbide. And you see it in industries such as automotive and in industrial applications. So traction inverters, you see a lot of silicon carbide. And high voltage applications above 600 volts, you'll see silicon carbide being something that's adopted quite a bit. For gallium nitride, you would see things that are kind of low to mid-range in terms of voltage. So things like chargers for laptops and small electronics where size and weight is very important. But in general, they're both slowly, definitely growing in terms of adoption, but silicon carbide is definitely the more mature one at this point. And I see the cost being a big factor as well. It's sort of one of those chicken and egg situations. The more people use it, the cheaper it's going to be. So if a lot of people, or if everybody uses gallium nitride or silicon carbide, then it becomes much cheaper. So it's a chicken and egg kind of situation.
Thank you, Steven. So as the silicon carbide and GaN devices become more accessible, so do you foresee that these solutions becoming standard or just for specific applications in the future?
I think they'll definitely become more standard. I think over a long period of time, it will definitely replace the traditional silicon technology that we have.
Okay.
In fact, my personal opinion is that I see GaN becoming that standard technology that's going to be used basically in entire industry. Right now, silicon carbide is definitely in the lead, I would say, but once people learn how to use GaN, once they figure out how to deal with the higher switching frequencies, how to deal with the tricky gate drive signals that comes along with using gallium nitride transistors, then GaN is going to become more widely used, and then it's going to become sort of standard, like the way silicon is in today's technology. So my bet is kind of on GaN in the long term.
Thank you. Thanks for sharing. So let's talk about model and simulation. So how has the role of modeling and simulation evolved in power converter design cycle? So if you think in practice about the complex topology that increased in terms during the course of year, but also the wide bandgap devices. So do you see also real-time co-simulations becoming essential tools for optimizing the design from efficiency point of view in power electronics?
Yeah, well, that's a great topic because as the product manager for a software design software, this is kind of what I live every single day. So, in power electronics, traditionally we have a less emphasis on simulation compared to other industries, but with gallium nitride and silicon carbide and wide bandgap technology, the need for modeling and simulation is going to pick up drastically. The reason for that is because if we look just at gallium nitride in particular, we're dealing with higher switching frequencies. And what that means is that your board is going to need to have very, very little inductance on that PCB. The way you do that is, you can't just do trial and error because that would take too much money, too much time. And this is where simulation and modeling comes in. If you can predict those parasitic inductance, you can do those simulation many times before you build that first prototype, then you can just really just save so much time and so much money in your design process. So I see the need for modeling and simulation becoming sort of like the tipping point for this mass adoption of wide bandgap. Once everybody designs with simulation in mind, I think that's really going to drive that adoption forward.
So in conclusion, Steven, my last one is about AI, so power electronics and AI. How do you envision AI impacting the broader power electronics market, or in particular, how can AI enable more autonomous decision making in power electronics design, but also testing?
Yep. So AI is on everybody's mind today, with ChatGPT, of course, coming out recently. And in software, it's a perfect place where AI can come into play. So for me, AI definitely comes into play when it comes to modeling. Modeling is really complex. We have tons of parameters for a single model. AI can do that optimization really easily. So that's one very specific area where AI can play a role. The other is with layout. Imagine if you can have a board where AI can do the layout for you, and it minimizes crosstalk, minimizes inductance, minimizes voltage spikes. If AI can predict all of that without you having to make those decisions, then that will drastically improve your design cycle and the time it takes to get your product to market. So I see AI as being a very positive thing when it comes to power electronics design.
So a lot of topics, not only AI and wide band gap.
Yes.
So, thank you, Steven. It's been a pleasure talking with you. Thanks a lot.
Yeah,
and
thank you, Mauricio.
Have a good day at PCIM. Thank you.
Thank you. Thank you, everybody.
Thanks a lot.